Students, in the last video we talked about internal energy, that is delta U equal to Q plus W. So I'll just make a quick revision of this point, that is in isothermal process, that is delta U equal to 0. So when you apply this condition to this equation where delta U is equal to Q plus W, so you will get W is equal to minus Q. For adiabatic process, this, in case of adiabatic process, here you can say that Q equal to 0. So this equation can be written as delta U equal to W or minus delta U equal to minus W. Third thing you can write, in case of isochoric process, where delta V equal to 0, so you can write delta U equal to Q at constant volume. Okay. Now the fourth thing you can write here, in case of isobaric process where temperature is constant, so you can write delta U equals to QP, that is heat is supplied or either heat is supplied or removed at constant pressure, equals to P delta V, or in terms of QP you can write here delta U plus P delta V. So these are the conditions for the isothermal, adiabatic, isochoric and isobaric process to know the values of delta U, and accordingly you can find out the values for W here. Now here comes the concept of this enthalpy. So what is this enthalpy? See, enthalpy is nothing but the sum of internal energy of a system and the energy equivalent to PV work, or in other words you can say that enthalpy is nothing but the heat supplied at constant pressure or heat removed at constant pressure here. So enthalpy, which is denoted by H, this is enthalpy. This is equal to sum of internal energy of a system. This is internal energy of system and the energy equivalent to, this is energy equivalent to PV type of work, pressure volume type of work. Okay, so you can write the same thing in mathematical way, that is H enthalpy, it is equal to U plus PV. Now change in enthalpy, that is delta H, is also a state function, means enthalpy is also a state function. Accordingly the change in enthalpy, which is denoted by delta H, it will be also a state function. So delta H will be equal to H2 minus H1, means the values of delta H, that is change in enthalpy, it depends on the initial and final states of the system. Means what is the value for enthalpy at initial state and what is the value for enthalpy at final state. If you subtract these two things, you will get change in enthalpy. So this can be written delta H is equal to H2 minus H1. Now further you can write H1 will be equal to U1 plus P1 V1 and H2 would be equal to U2 plus P2 V2. So we reach up to this state. Now what is this delta H? This is difference between H2 and H1. So you can write further here, that is delta H equals to delta H, this is equal to U2 plus P2 V2 minus U1 plus P1 V1. Okay, so you can further simplify this as U2 minus U1, put it in bracket, plus P2 V2 minus P1 V1. So this can be written as U2 minus U1 means delta U plus P2V2 minus P1V1, that is the change in pressure and change in volume. It can be written as delta into PV. So for constant pressure, now as I already told you, for this internal energy, that is change in internal energy, can be determined by knowing the initial and final state. But you will be aware only about the change in the internal energy. You will not be aware about the initial value for this internal energy and the final value for the internal energy. I gave you the example of bank account also. So here you can write further for at constant pressure. Means at constant pressure, what will happen? At constant pressure, that is P1 would be equal to P2, which you can denote as capital P. So you can write delta H equals to delta U plus P will remain constant for this equation, delta V. So you reach up to this equation, that is delta H equals to delta U plus P delta V. So what is this delta H? This is change in enthalpy. This is the addition or sum of internal energy of a system. Means what is the amount of heat you are supplying, that will increase the internal energy, or if it is heat is released, that will decrease the internal energy, plus the pressure volume type of work done on the system or by the system. Accordingly, you will get the value for this change in enthalpy. Means this is actually, as I already told, that enthalpy is nothing but the total heat content of the system. Now here again, if this is equation number 1 here. If the pressure inside and outside the system is same, means if P external equals to P inside and outside is same, it means that P external would be equal to P. So you can write for this QP equals to delta U plus P delta V. So when this pressure is constant, means if the external pressure and the pressure of the gas, if two things are same or equal or constant, this delta H would be equal to heat supplied or removed from the system at constant pressure, that delta H equals to QP. So we have arrived this situation where there is a constant pressure here. So you can see here the things are already displayed over here. So you can have this condition that delta H equals to QP when the pressure is constant. This P stands for constant pressure, means the process would be isobaric process. So for this isobaric process, this would be delta H is equal to QP. So you can write this as equation number 2 here. So from equation 1 and 2, what you can write, that is delta H equals to QP, because delta H is equal to delta U plus P delta V and QP is also equal to delta U plus P delta V. So delta H will be equal to QP. So this is change in enthalpy of the system. This is change in enthalpy of the system. Change in enthalpy of the system will be equal to heat transferred at constant heat transferred from system at constant pressure, that is H and Q, that is enthalpy and heat. These are the state functions. So you can write these are as a state function, means the values of these are dependent on the state of the system, that is H and Q. This is enthalpy and this is heat supplied or removed from the system. So further you can go for the next thing, that is relationship between delta H and delta U. So relation between delta H and delta U for chemical reactions. for chemical reactions. So you can write at constant pressure. You will have to put some condition. At constant pressure, that is if the process is isobaric. So you'll have this equation in front of you, delta H equal to delta U plus P delta V. Delta H is equal to delta U plus P delta V. So for the reactions in which solids and liquids are involved, for the reaction where solids and liquids are involved, they do not show change in volume. They do not show volume change. Do not show volume change. There might be a change, but that can be very, very small, and that can be neglected also. Means if the reaction is carried out at constant pressure, means isobaric condition. These are the reactions which we always carry out in chemistry laboratory. So for the solids and liquids, there is no change in the volume. It might be there, but that is so very, very small that it can be neglected here. So if you neglect this, if you say that delta V equal to 0 here, so you'll get delta H would be equal to delta U. This is for solids and liquids. The condition should be that delta V should be equal to 0. And when would be delta V will be 0? When the process is isobaric. So this change would be 0, and you will get this situation here. Now for the second thing, we can write for reactions involving gases, delta V cannot be neglected here. So you can't neglect delta V in gaseous condition. So for this one, for gases, you will write delta H equals to delta U plus P delta V. Isn't it? So you can further write as delta U. This is delta V, means change in the volume. So you put the pressure outside, because pressure is supposed to be kept constant because it is an isobaric process. So V2 minus V1. So for the delta U plus, now solve the bracket, PV2 minus PV1. So this would be your equation number 1. So what is this V1? V1 is the volume of gas phase of the gas phase reactants. Means this is the volume of reactant and this is for the product. So V1 is the volume of gas phase reactant. Gas phase reactant. And V2 is the volume of, this is volume of gas phase products. So we assume that reactant and product, these behave ideally. So you can apply ideal gas equation here, which is PV equals to nRT. So this is your ideal gas equation. If we apply this ideal gas equation, where this N will be the number of moles. So N1 you can say number of moles of gaseous reactant, number of moles of gaseous reactants, and this N2 would be number of moles of gaseous products. Now when you are applying this PV equal to nRT to this equation, you will get PV1 equals to N1RT and PV2 would be equal to N2RT. So this would be your equation number 2. Now substituting equation number 2 in equation 1. We have got this equation as equation 1. So substitute the values of PV2 and PV1 in this equation. So you'll get delta H would be equal to delta U plus N2RT minus N1RT, isn't it? So further, if you simplify it, this is very simple. Delta U plus N2 minus N1, put it in bracket, and outside the bracket you will have the constant things. So finally you will get the equation delta H equal to delta U plus N2 minus N1, means delta N of the gaseous. So G stands for the gas phase reactants and products into RT. So this equation is very much needed to solve the problems based on to find the enthalpy change in the gas phase reaction. Okay, where this delta N is the number of difference between the number of moles of product and those of the reactant. So delta N is nothing but this is the difference between number of moles of product, that is N2, minus number of moles of reactant. So by looking at the reaction, you can very easily calculate the number of moles of product and the reactant and substitute the values here, and you can get the change in enthalpy for the reaction. Now here there is one question can be asked: at what conditions delta H would be equal to delta U? Delta H would be equal to delta U. So the answer for this you can write: in solid and liquids where there is no change in the volume, delta H would be equal to delta U. We had talked about this earlier also. When delta V equal to 0, when this delta V will be equal to 0, when there is no volume change and at the constant pressure also. So don't forget the conditions. Conditions are very, very important here. So at constant pressure means at equilibrium also. That is thermodynamic equilibrium. So delta H would be equal to delta U. Now for the work done in chemical reactions. Work done in chemical reaction. Work done in chemical reaction. So if a reaction is given, so you will be aware about when you will be aware about the reaction, you know the reactant, you know the number of moles of reactant, you know the number of moles of product forming. So you can calculate everything and you will be aware about the work done. So for this, the condition, if the process is isothermal, for the isothermal process, how will you calculate the work done in chemical reaction? Isothermal process means at constant temperature and pressure. The condition is very important here. The temperature should be constant and the pressure should also be a constant one. Now when these are the conditions for the any given chemical reaction, you can calculate W equal to P external into delta V. So assuming P external equals to P, means what? Here you can write W equals to minus P delta V. So minus P, now what is this delta V? This is V2 minus V1. So this you will get here minus PV2. So minus minus it will become PV1. So you get the equation. Here you can write negative sign actually. P external equal to P, we can't replace this negative sign actually. So here W equal to minus P delta V minus P V2 minus V1. So you will getting minus PV2 plus PV1. So if the gases were ideal, PV1 equals to N1 RT and PV2 would be equal to N2 RT, isn't it? So at constant temperature and pressure, so the condition will remain same at constant temperature and pressure. So W will be equal to minus, what is this, PV2, that is N2 RT. So substitute here N2 RT. Here PV1, that is N1 RT. So plus N1 RT, isn't it? Now simplify this, put this negative sign outside the bracket, so that you can write N2 minus N1 into RT. So further this would be equal to minus delta N, the difference between this gaseous moles of the product minus gaseous moles of the reactant, that will give you delta Ng. G stand for the gaseous phase of the reactant and product, into RT. Temperature would be constant here. So the sign of W depends on sign of W, that is work done. It will depend on delta V. So W depends on delta V, that is change in volume here. Now the first condition here, that is if N2 is greater than N1, then delta Ng would be positive. If this is positive, W would be negative here. Okay. Then next it means that work is done by the system. When W is negative, work is done by the system. Of course, on the surrounding. Means this is the work of expansion. This is work of expansion here. Second thing, if N1 is greater than N2, so delta N, that is difference between this, that is delta N, would be negative and W will be having the positive value. So W is positive here. So when W is positive, it means that work is done on the system. It means that work is done on the system. Okay. So the third thing may arise, that is if N1 equals to N2, so in such cases delta Ng, it would be 0 and W will also be equal to 0. So these are the three things. When N2 is greater than N1, this is negative, this is work of expansion. If N1 is greater than N2, delta Ng negative, W is positive, and if N1 equals to N2, this will be 0 and work done also would be equal to 0. It means that no PV work is done when number of moles of reactants and products are equal. So no work is done. Now remember, here process is carried out at constant temperature and pressure. So don't forget this condition. Reaction is carried out at constant temperature and pressure. Then only these things will arise here. Okay. So thank you. In the next lecture, we will talk about the enthalpy of phase transition.